Howdy. We are analyzing an RC circuit, which you see drawn in front of you, and you see the questions that we'll be dealing with. We're dealing, first of all, with charging the capacitor, which means we're going to close this switch marked S, and we will define that as time t is equal to 0, so we'll start timing after that. So switch closed at t is equal to 0, so that's when we start running current through the resistor and charging the capacitor, both at the same time. And we're going to find two things. One is, what is the charge on the capacitor as a function of time? That's the first question here. What is Q as a function of t? And then once we do that, we will find I as a function of t. What is the current through the capacitor as a function of time? We'll find one and then the other one. Okay, so we are going to do that by, first of all, analyzing the circuit at some time t after we've thrown the switch. And at that time, there is current going through the resistor, so I'm going to actually draw the switch as being closed, which I have to do very low tech. The switch is closed, and at some time later, we have current going through the resistor, and we have some amount of charge building up on the capacitor. So this is at some time t. And we're going to analyze the changes in potential as we take a walk around this circuit, and recognizing that if we start and end in the same place, which of course has to be in the lower left-hand corner, and go clockwise, that all the changes in potential have to add to 0. So let's start. Okay, so we're going to travel vertically up from point X, and we travel first of all through the EMF, and that's an increase in potential plus E. I know it's an increase because I'm going from the negative to the positive plate. I travel along, and I'm now so I'm going to draw this dotted line. So I now get to the resistor. There's no change in potential across all that beautifully resistance-less wire, but now I get to this resistor. I'm traveling in the direction of the current, so I'm losing potential energy for my mythical positive charges, so I'm going to a lower potential, so I say minus V across the resistor. I continue, I go across this capacitor, and I'm going from the positive plate to the negative plate when I go from right to left, and so I'm decreasing potential. The positive plate's at the higher potential, minus Vc, and then I get back to where I started, and that is equal. So all the changes add to 0. Okay, so now I'm going to say that for any resistor with current, the potential difference across it is I times R, and for a capacitor with a charge on it, the potential difference across it is Q over C. And again, I'm going to use actually small q over C because that's a variable amount, as opposed to capital Q, which we might reserve for the total amount of charge on the capacitor when it's all charged up or something like that. So, and now I'm going to drop things, and then I'm going to sub in. So I have E minus I times R minus Q over C is equal to 0. And then I'm going to use one other identity, and that is that the current through the resistor is dq dt, the rate at which current flows through the resistor. And so I'm going to sub that in, and I'm going to also this time write my small case q. So this is dq times dt times r minus small case q, variable amount of charge q over c is equal to 0. All right. I need to solve this equation to find Q as a function of t. That's the first thing I'm going to do. And as I have possibly mentioned, my strategy is to get the coefficient of Q to be positive 1. So that means I'm going to multiply every term on each side by negative c times negative c. Okay, so that means I'm going to get negative EC plus RC dq dt plus Q is equal to 0. Okay, I'll do a little bit of rearranging, and what that is going to involve, first of all, is I'm going to take what I'm shooting for right now, by the way, my goal is to get all the Q stuff on one side of the equation and all the T stuff on the other side. Separation of variables, I believe they call it. So I'm going to start that by taking this term and subtracting it from each side. And I'm also going to take my negative EC plus Q and write that as Q minus EC equals negative RC dQ dt. So I now have all my Q. I've got this function with Q in it, Q minus EC. EC, of course, is a constant. I want to group that with my DQ. So I'm going to divide each side by Q minus EC, which is going to give me, so I'm going to divide by Q minus EC, divided by Q minus EC, which is going to give me 1 on the left equals negative RC, and I'm going to put that over dt. I'm going to pull that term out, and then I'm left with dq over Q minus EC. Okay? These terms are multiplied by each other on the right-hand side, multiplied, multiplied. So I'm going to divide each side by this negative RC over dt term to get it over to the left-hand side. And that leaves me with negative dt over RC is equal to dq over Q minus EC. Okay, this has been a bunch of algebraic rearrangement that gives me all the time stuff on one side and all the charge stuff on the other. All right, now I'm ready to actually find out what Q is as a function of time, and so I'm going to integrate each side. I could sing, but for some reason I'm not going to. I'm going to treat this as a definite integral that starts at t is equal to 0 and until some time t. So the end of the span of time is a variable amount of time, depending on how long I want to let this thing charge up. But that means that for my limits, I want you to recognize that I'm putting different letters down for my limits, but they're going from the same point to the same point. From the beginning, where t is equal to 0, until the end, when t is equal to t. And over here, I'm integrating with respect to Q, so I start when charge is 0. I put 0 there because at time t equals 0, there's no charge on the capacitor. So that's actually, I could say that that's equal to charge, 0 is equal to Q, until later when I have some amount of charge Q on the capacitor. All right, I'm just going to erase that. Okay, so now I can integrate, which makes me happy. And I do this by the normal methods. I'm doing this as a definite integral. The one on the left is a constant times dt, so the integral is just t with a constant thrown in. So the integral is negative t over RC. I'm treating this as a definite integral, so I'm integrating from 0 to t. On the right-hand side, I'm integrating du over u, and the integral of that is natural log of u. And so I'm going to write natural log of Q minus EC, and I'm integrating from 0 to Q. Okay, so I'm going to plug in my limits of integration. On the left-hand side, fairly straightforward, but I'm going to write it out. Negative t over RC minus 0 over RC, negative 0 over RC, equals, on the right-hand side, natural log of, okay, I'm plugging these variables Q and 0 in for Q. So the first term is going to be Q minus EC, and the second one is going to be natural log of 0 minus EC. Okay. On the left-hand side, I have minus 0 over RC. That term, of course, is 0, so I just have negative t over RC. And on the right-hand side, I'm going to take advantage of the fact that natural log of A minus natural log of B is natural log of A over B. So this turns into Q minus EC over 0 minus EC. And then I am going to simplify this, what's in the brackets on the right-hand side, in the green box here, is Q minus EC over negative EC, which is the same as negative EC plus Q over negative EC, which is the same as negative EC over negative EC, which is 1, plus Q over negative EC, which is minus Q over EC. So that's how I did that earlier. And so I now have negative t over RC is equal to natural log of 1 minus Q over EC. And now I raise both sides to the power of E. No, that's not. I raise E to the power of each side, which which means I have e to the negative t over rc is equal to e to the natural log of 1 minus q over ec, which is just 1 minus q over ec. Okie doke. I'm trying to isolate q. So I'm going to isolate the q over ec term. And I'll do that by adding it to each side and then subtracting this from each side. So I'm going to have q over ec equals 1 minus e to the negative t over rc. And finally, I just multiply both sides by ec times 1 minus e to the negative t over rc. And there is my charge as a function of time. It makes me happy, and I know that it yields me a graph that q as a function of time is going to look like this. It's going to be asymptotic to this value, and that value is EC, which is the amount of charge on the fully charged cap. So I am done.